Hi, my name is Matthew Paulsonelli,
Hi, my name is Jiacheng Tian.
and this is our presentation on our project Grid Attack, a tabletop arcade. Let's dig in. So, Grid Attack is our final project. It's a tabletop game that brings the classic game of Battleship into the modern world using embedded systems. We wanted to display how microcontrollers like the ESP32 can handle complex and synchronized gameplay while also dealing with multiple inputs and outputs. Our design combines hardware and software seamlessly, from the joysticks and the touch sensor to OLED displays and the LED matrices, as well as an IoT dashboard for remote control and monitoring. This project isn't just about having fun. It demonstrates the growing role of microcontrollers in everyday solutions and showcases what we've learned as ECT students in our final semester. Before beginning construction of our game, we researched several other similar projects to see how they interpreted the game. Some used breadboards and CRT displays, and some used multiple LED matrices or even VR hybrids, but they didn't achieve a synchronized two-player system like Grid Attack did. Grid Attack improves on these two by using two ESP32s with custom PCBs and a fully enclosed 3D printed model. We added RGB lighting, audio feedback, and usage of an IoT dashboard to make the game experience perfect and reliable. Beyond this, we also researched communication protocols, PCB design practices, and user interface elements to ensure our project was full and user-friendly.
Our project is a tabletop game of Battleship. It's designed for two players sit and play in face-to-face. Players play the game using joystick for a sensor and keypad, and the feedback comes from the LEDs and audios. We have two ESP32s to keep the game always synchronized, and the IoT dashboard can provide the control system and the remote monitoring. Our Grid Attack is built on a custom PCB with the enclosure in a 3D print housing that make it to a complete and professional project.
Here's a picture of our completed build with all of the parts installed. There's also an additional LED diffuser plate that's been placed over the matrix just to soften up the LEDs, but you can see the gameplay in action, the 7-segment display being used, the OLED displaying its screen for the state that the game's in, as well as the installed joystick, matrix, and the touch sensor.
Our project has 4 inputs: number pad, joystick, touch sensor, rotation knobs, and 5 outputs: LED matrix, 7-segment display, RGB LEDs, OLED screen, and speaker. And we are using ESP32 as our MCU. Each set has one full set of MCU and inputs and outputs. Schematics. This is our electro wiring diagram. This shows one side of the circuit with all components and MCU in it. And this is our schematic of one-side circuit developed by Fusion. This is our PCB design. The left one is bottom copper and the right one is top copper. And this is our PCB design diagram on Fusion. It's a double-sided PCB with complex circuits. Each set of systems will use one identical PCB. And this is our final soldered PCB. The left shows the bottom of the board, and the right shows the top of the board.
Here you can see our 3D model designed in Fusion. On the left, you can see one half of the enclosure, which is printed on its own. On the right, you can see a fully completed finished model of what they would look like when it's put together with some of the components modeled in there. And at the bottom in the center here, you can see the base plate with the clips that will hold the PCB and the power board, as well as a few holes on the side just so that they mount into the holes on the sides of the enclosure. So here's our mechanical design diagram for our full enclosure developed in Fusion. The top right, you'll see the parts list with every single part number, the quantity of each, and what its ID part number is for this diagram. So if you take a look here, you can see Number 1, it points to the 7-segment display, and that's shown in the full view of the 3D printed enclosure. And then there's a couple other views for the front, left, and top, which will show all the dimensions of every cutout, every side, and every angle. What you can see here is that it's 310 millimeters long by 210 millimeters wide, and it's also 188 millimeters tall. So now that we've got a view for the design of the project, we're going to look at some of the hardware that's included. First up here, we've got the microcontroller we chose and the power supply. We chose the ESP32 S3 Dev Kit C. The reason for this is because this specific model of the ESP32 has enough GPIOs for our project, because our project is very GPIO heavy. This microcontroller is great at real-time processing, and it comes with built-in Wi-Fi, which helps to host the IoT dashboard. One of them acts as the central game controller. It hosts the IoT, the volume, and the DF player with the speakers. The other one also acts as a central game controller, but it takes orders from the first one. So one's a host and one's a client. These two work together to synchronize the gameplay between the boards, and they converse via UDP over the shared Wi-Fi network. Next up, we've got the voltage regulator. This regulator just takes any voltage from 6 to 36 volts, and it regulates it down to a stable 5 volts. The reason we chose this one in particular is because it has a strong enough output, and it doesn't diminish the current. So our power supply is a 12 volt 2 amp power supply, and when plugged into this voltage regulator board, it outputs 5 volts at roughly 4.8 amps, which is more than enough to power all of our peripherals, the LEDs, the LED matrices, and everything all at once without problem. Next up here, we've got the logic level converter, and this one here is just a bidirectional voltage level shift. It can go from either 3.3 to 5 volts or vice versa. And this one's necessary as some of our peripherals require 5 volt signal, and the ESP32 only outputs 3.3 volt signal. Those are like the LED matrices, the RGB LEDs, as well as the DF player module, which takes 5 volt signal. Next up, we've got some of the outputs here. So I'm going to list off our outputs from top to bottom here. We've got the speakers, the RGB matrices, the OLED display, the 7-segment display, the RGB LEDs, and the audio chip, the DF player. So starting at the top here, the speakers, self-explanatory, they're just to play sound. They go hand in hand with the DF player here that has a micro SD card installed on it with sounds relating to our game. And when it's commanded to, it outputs those sounds through the speakers. The DF player uses a TX and an RX to converse with the ESP32, and it just takes single commands to either play sound, stop sound, etc. The RGB matrix here is just a 10 by 10 array of WS2812B LEDs. It's got three pins, one for voltage, one for GPIO, and one for ground. The purpose of this board here is just to show the game pieces. It's the main game board, and as the pieces are in a grid format, this is the perfect solution. Next up, we've got the OLED display here. It's 176 by 176 pixels. It takes SPI to control it, or we're using SPI to control it. And the purpose of this is just to show minor state updates for the game. So it shows game settings at the beginning. It tells you when to place your ships. It just shares information with the user about how the game is going. The 7-segment display here takes 4 GPIOs each into shift registers on our custom PCB. It has a 2-digit shift to display its numbers, and it's just to show the score, sorry, not the score, the timer of the game. It'll count down from whatever setting you've selected. If you selected 30, it'll start counting down from 30 seconds once your turn comes around. And next up, we've got these RGB LEDs. They're pretty self-explanatory. They're similar to the RGB matrix, whereas they only have 3 pins. Well, 4 pins. One's digital in, one's digital out, and the other 2 are VS and ground. And the digital in of the first of a pin connects to the digital out of the last pin, meaning you can daisy chain these into theoretically an infinite loop, but in our case it's up to 10 on one side of the board. The purpose of this is just to show ambience. When somebody's ship gets hit, their side will light up red, and when you hit the other ship, out of the other player's ship, it'll light up green for you. This is just to show a little bit of color around the board. All right, and next up we've got the inputs. So first input we have is the number pad. It's just a 4x3 number pad. It takes 7 GPIOs, 1 for each column and 1 for each row. And all it is just an array of buttons that convert presses into digital signals. We use it for selecting game settings at the beginning, choosing some options, and like rotating ships. Next up, we've got the joystick. This is a pretty simple joystick. It's not an analog joystick. It actually uses 4 limit switches. So it's strictly digital, and it's perfect for our application here, where we only have 4 directions to use. All it does is it controls either the cursor when you're playing the game or the placement of your ships when you're in the placing stage. That's then paired with the touch sensor, which is counting as a select button here. It's a physical touch sensor. The harder you press, the harder it registers. In our game, we've set it fairly high so it doesn't register accidental presses. And all it does is it confirms your selection or confirms your shot when shooting. And lastly, we have the rotational potentiometer. This is just the volume control. This is interpreted by the ESP32 to different ranges of the voltage, and it will just convert that into a number, say 15 as the volume level, and it will send that via command to the DF player. It's a 10K potentiometer, and it takes the 3.3 volts as its voltage. So it just varies the voltage between 0 and 3.3, and that's how the ESP32 interprets it. Now that we've talked about the hardware, let's talk about the software. All right, so first up, we've got the development stage here. To begin developing, we started with VS Code. It's very easy, it's simple to work with, and it has a modular workspace for having multiple files, which our project does. Its interface allowed us to keep that organized and clear, and to pair with that, it goes along with Platform I/O, which is integrated into VS Code and gave us powerful support. Platform I/O can handle many ESP32 libraries. It auto-downloads them, it'll automatically configure the boards, and it's very efficient for flashing the ESP32s. This is a major reason that we moved away from Arduino towards Platform I/O, which performs better for more complex tasks like this. Additionally, we use Copilot as a coding assistant. It can easily scan through code and help us solve problems faster. It clarifies syntax, and it can give us quick references when we debug for multiplayer synchronization. They saved so much time and let us focus on other aspects of the code and other aspects of the design. So next up, we've got the IoT elements. Both of the ESP32 boards are connected to a Wi-Fi network, which allows them to both communicate effectively between each other and also allows for the hosting of the IoT dashboard. To communicate from ESP32 to ESP32, we use the UDP protocol, which is very easy, transfers over Wi-Fi, and it uses flags to converse between each other, the game state, and other necessary variables. The dashboard is hosted by only the player 1 ESP32, and it maintains the live state by constantly checking the game state from the board and pushing it to the web page consistently. All of the game's variables and information that's relevant to the IoT dashboard has been serialized to JSON, and that's how it's printed to the IoT dashboard.
This is our details of the dashboard. You can see the player scores, the board status, the time left for each round, and the legend of the board. And you can check the connect status at the top right, and the current game status, and the setting tables, like the sound, item cards, the round time, and number of votes. And you can control to restart game or reset game, power on or power off. We have encountered many different problems while designing and building our project. First, when we came up with the idea of the project, we were concerned about the power management. The components like OLED and LED matrix might draw a large amount of power. Because this is a tabletop game, we want to make it portable and simple for users, so we keep a small power supply and only one power cable. After we research our components, we calculate the absolute maximum current that need for the operation. So we choose a voltage regulator that converts voltage from 5 about to 36 volts down to a stable 5 volts and 5 amplifier for the project. This solves the power management problem. The second OLED display, in the early version, we used I2C for communication between ESP32 and OLED to read the display the text. After we tested, we found that updating speed of the OLED is too slow than expected. And it also caused a halt in the game system during its update. Because OLED updates pixel by pixel, we decided to use SPI, which is Serial Peripheral Interface, that supports much higher data transfer rates than I2C. And also, the rendering took a lot of CPUs that would slow down the entire system. So we decided to use the created image of text and store them into ESP32 instead of render the text. This makes the OLED screen update much more faster. And third, after we make everything work for one set, we start to make the communication between two ESP32s. This is only one ESP32 handles the IoT dashboard and the main game logic, so it was challenging to transfer from one ESP2 to another one for game data. At first, we used ESP now as a protocol, but it throws problems when transferring the game states and messed up with the player turns. It always has package loss and a unstable system when running the multiple thread events. To solve this, we use a UDP protocol transfer data. We made many flags to represent different states, for example, a text state, setup state, placing board state. This flag and data will be sent from one to another completely. In this way, the game will have less or no bugs because of data transfer. Also, using flags to transfer the data is easier to upload and update the IoT dashboard in real time. For this course, we have learned many meaningful lessons, and we want to share it with students who take TPJ for next semester. First, do enough research before starting anything. Our project has a lot of different inputs and outputs that requires different voltage and variant currents, which was a hard time for power management. So it's important to do the research and check all components datasheet before choosing the components and building the circuit. In this way, it will largely reduce the time spent on troubleshooting on hardware. Second, find alternate solutions for a problem. Don't always stuck at a problem. There are always many different ways to solve it. For example, we choose SPI instead of I2C for the OLED display, and we found that it works perfectly with updating the images and rendering the text. Third, is very important, push everything ahead of the schedule. Even though we almost finish everything on time, there are still a lot of unexpected issues happens that could delay our design and progress. So we learned that it's better to make a schedule and finish the task 3 to 7 days earlier whenever possible, in order to avoid any accidents. And it's also meaningful to us in our future works. Now let's look into future changes and improvements. if we have 6 more months? What can we improve? Currently, our game may lag because of multiple tasks run at the same time, because the ESP32 does not have enough RAM or CPU for that. We could use a better microcontrollers like STM32H7XXM. It has 400 MHz and 1 MB RAM, which is sufficient for multiplayer game developing. It has 100 pins that our project can be built using only one microcontroller. The drawback is it doesn't have Wi-Fi or Bluetooth. We have to use external Wi-Fi module for that. But overall, it's cheap, and we believe that a single 100 pins microcontroller would perform more effective for game operations than transferring between two separate microcontrollers. Another option is using two Raspberry Pis to transfer data. It's more expensive, but it has a higher and stable performance and a larger storage than these typical microcontrollers. It runs a full Linux OS, which can install recursive files and libraries with a single command. And it also supports HDMI for better visuals for game or development. It has a higher speed built-in Wi-Fi and Bluetooth, which is easy for wireless communication and support remote development. That means no wires is needed between developer and the Pi. The debugging or building can be done without opening the enclosure. Another improvement if we have 6 more months is our components is enough to support other grid-based games. User can have more options to the tabletop games. There can be guessing games like Battleship, which we already did, or logical games like Ultimate Tic-Tac-Toe and Reversi. These games can be implemented simply using the code. For Tic-Tac-Toe is a 9x9 grid game that expands from a classic 3x3 Tic-Tac-Toe. It contains a large board and 9 mini boards. The rule is basically make 3 marks in a row or column or diagonal. But in the Ultimate Tic-Tac-Toe, player will win the mini board to get a big mark in the large board. The game first starts in the middle mini board, and the next movable board will depend on where the previous move in the mini board. For example, if player 1 make a move on the top in the mid mini board, the next player will be able to move in the top left mini board. Another example is Reversi. It's an 8x8 grid game. The rules are easy. Just sandwich components piece to turn their piece into yours, like from black to white. And don't let opponents get to the corners because they will win easier. And this is our reference. Thank you.